Hello everyone! Welcome to Math Ed 807 Discrete Mathematics 2 class under Dr. Alan Reyes. This is Miss Melanie Matilia Lalim, your presenter for today. We will be discussing permutation, combination, and binomial coefficient. In this presentation, expect that you will learn how to illustrate and define permutation, combination, and binomial coefficient, differentiate permutation and combination, identify situations when a permutation, combination, or binomial coefficient can be used, and solve probabilities using permutation, combination, or binomial coefficient. To start, let us analyze these two statements. Number 1, my fruit salad is a combination of apples, grapes, and bananas. Number 2, my 4-digit employee identification code is 8163. Notice that in statement number 1, it doesn't matter whatever order the fruits are in. They could also be bananas, grapes, and apples, or grapes, apples, and bananas. It's the same fruit salad. In statement number 2, the order does matter. 8163 should be used the same because 8136 won't work, nor 1836. It has to be exactly 8163. The various ways in which objects from a set may be selected, generally without replacement, to form subsets may be described using either a permutation or a combination. Both permutations and combinations are ways to count possibilities. Both refers to groups or arrangement of objects. However, there is one big difference between them. When dealing with combinations, the order of objects is not important, whereas in permutations, the order of objects is important and makes a difference. Let us try to identify whether the following is a permutation or a combination. Number 1. Your locker combo is 0616. Is this a permutation or a combination? You are correct. This is an example of permutation since the order is important. You cannot open your locker if it is not exactly 0616. Example number 2. The lottery numbers are 6, 23, 14, 21, 16, and 20. Is this a permutation or a combination? You are correct. This is an example of a combination. You can win the lottery if you have the given numbers in any order. Thus, the order of the objects is not important. In answering permutation or combination problems, it is very important that you know how to tell whether the order is important or not. Next, you should be able to identify if repetition of objects is allowed or not. Let us explore theorems involving permutations and combinations and the formulas to be used. The first formula is for calculating the number of permutations of n objects with no repetitions allowed. The theorem states that the number of permutation of n distinct objects taken all together is equal to n factorial, where n is the number of objects. The second formula is n raised to r, where n is the number of things to choose from and we choose r of them. We use this for calculating the numbers of permutations of r objects from n objects with repetitions allowed. The third formula is for calculating the number of permutations of R objects from N objects with no repetitions allowed. The theorem states that the number of permutations of N distinct objects taken R at a time is equal to N factorial all over N minus R factorial. Instead of writing the whole formula, people use different notations such as this. We also have the circular permutation. This states that the number of N objects arranged in a circle is equal to N minus 1 factorial. The last theorem states that if among N objects, R sub 1 are identical, and another R sub 2 are identical, and the remaining, if any, are all distinct, the number of permutations of these N objects taken all together is equal to N factorial all over R sub 1 factorial multiplied by R sub 2 factorial. Now, for the combination formulas, there are only two. In the first formula, repetition is not allowed when calculating the number of combinations of R objects chosen from N objects. So the combinations of R objects chosen from N objects is equal to N factorial all over R factorial multiplied to N minus R factorial. In the second formula, repetition is allowed when calculating the number of combinations of R objects chosen from N objects. The combinations of R objects chosen from N objects is equal to N plus R minus 1 factorial all over R factorial multiplied to N minus 1 factorial. Don't worry if all of these different formulas seem to be hard to remember. You can take a moment to pause this video and copy each formula. To understand these theorems better, let us solve some problems applying the formulas mentioned. But you need to take note of the following. First, make sure to tell whether the order is important or not. In other words, identify if the problem is a combination or a permutation. Number 2, determine if repetition is allowed. Number 3, use the appropriate formula based on what you found in the second step. Number 4, substitute known numbers for the values in the formula and perform the operation. Let us try to solve example number 1. How many distinct ways can the letters of the word column be arranged? Let us start by determining if we're dealing with permutations or combinations. To do this, consider the arrangement COLUMN and the arrangement MUNCOL. We see that these represent two different arrangements, so the order of the letters makes a difference. Therefore, we can say that we're dealing with permutations. Now, we must consider if repetition is allowed. When we create an arrangement of the letters, we put one letter in the first spot, then the second spot, and so on until all 6 spots are filled. Once we put a letter in a spot, we can't put it in another spot because it's already been used. Therefore, repetition is not allowed. In addition, we know that we're dealing with a permutation of 6 objects since the word column has 6 letters, and repetition is not allowed. Therefore, we will use the formula n factorial. Substituting 6 to n, we get the following. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is equal to 720. Therefore, there are 720 ways to arrange the letters in the word column. Let us have example number 2. How many 3-digit numbers can be formed from digits 3, 7, 0, 2, and 9? Let's consider the 3-digit number 702 formed using 3 of the 5 digits. If we change the order to 207, this represents a different number. Therefore, order makes a difference. So we're dealing with permutations. Now, we can make the number 777 using the 5 given digits, because 7 is one of the digits and it is not specified that repetition is not allowed. Therefore, repetition is allowed. We see we have a permutation of 3 objects from 5 objects where repetition is allowed. Therefore, we use the formula n raised to r, where n is equal to 5 and r is equal to 3. Plugging these values will give 5 raised to 3, which is equal to 5 times 5 times 5, and that is equal to 125. Therefore, we can make 125 3-digit numbers from the numbers 3, 7, 0, 2, and 9. In example number 3, you are to select 3 representatives from a group of 20 people. How many ways are there to do this? If we select 3 people, say Mark, MJ, and Ferdy, it's still the same group if we said we selected MJ, Ferdy, and Mark. Therefore, order is not important. So, we're dealing with combinations. In addition, once we have selected a person, we can't select them again since they are already in the group. Therefore, repetition is not allowed. Based on this information, we use the formula the combination of n taken r at a time is equal to n factorial all over r factorial multiplied to n minus r factorial. Substituting 3 for r and 20 for n will give us the following. Therefore, there are 1,140 ways to choose 3 representatives from a group of 20. Example number 4. There are 9 car racers. In how many ways can the first 3 finishers come in? Analyzing the given problem, we can consider car A, B, and C finishing in that order. Now, consider those same car racers finishing in the order C, A, B. This is a different order of finishers. So, we see that the order makes a difference. So, we're dealing with permutations. Now, consider racer A coming in first. That racer has now finished. So the racer can come in second, third, and so on. Thus, repetition is not allowed. We are dealing with permutation of 3 of 9 objects, where repetition is not allowed. Therefore, we use the formula, the permutation of n taken r at a time is equal to n factorial all over n minus r factorial. Substituting 3 for r and 9 for n will give us the following. Therefore, there are 504 ways for the top 3 finishers to come in during a race with 9 participants. Example number 5. In how many ways can 5 different trees be planted in a circle? Notice that we have the word circle. Therefore, we will use the circular permutation, which states that the number of n distinct objects arranged in a circle is equal to n minus 1 factorial. Substituting 5 to n as the number of objects, we get 5 minus 1 factorial, which is equal to 24. Therefore, there are 24 ways of planting different trees in a circle. This time, let us discuss binomial coefficient. Binomial coefficient is related to combination, but it counts certain ways of grouping items. Specifically, binomial coefficient counts the number of ways to form an unordered collection of k items chosen from a collection of n distinct items. For example, if you wanted to make a 2-person committee from a group of 4 people, the number of ways to do this is C for 2. Incidentally, there are 6 ways. Just label the people A, B, C, D, and list all the 2-letter sets AB, AC, AD, BC, BD, and CD. Remember, order doesn't matter. So BA is not different than AB. So we know that C for 2 is equal to 6. There are many different notations used for the binomial coefficients. All of these are equivalent to C and K and may be read as N choose K. The last notation, the one that looks a bit like a fraction, is one of the most commonly used, though you will see N choose K fairly often because it's easier to type. To compute for binomial coefficient, we use this formula. N choose K is equal to n factorial all over k factorial multiplied to n minus k factorial. To understand this better, let us try to solve a problem. How many different 5-card poker hands are there? Well, we need to know that there are exactly 52 cards, not counting jokers, in a standard poker deck. Once the cards are in your hand, it doesn't matter what order you put them in. So this is exactly the right kind of problem for binomial coefficients. We have to compute 52 choose 5. Now in this case, we must use the shortcut formula because 52 factorial is such a huge number that most calculators cannot store it properly. Note that n minus k plus 1 is equal to 52 minus 5 plus 1, which is equal to 48, which will be the last factor in the top. Plugging in the values 52 and 5 will give us the number 2,598,960. Therefore, there are 2,598,960 different poker hands.